Hey guys, welcome back to geometry. The last couple of times we were together, we were talking about conditional statements. So we had the original conditional statement, which was if P then Q. We had the converse, which was if Q then P. We had the inverse, which was if not P then not Q. And we had the contrapositive, which was if not Q then not P. Well, today what we're going to get into is another form called a biconditional statement. Now, originally I wanted you to just research this on your own, but then I decided I'm going to walk you through some of the finer points. So let's still use the internet to help us find stuff. If we don't know what something is, use our old friend Google to look it up. So biconditional, spell it correctly helps. Yeah, there we go. Biconditional statement. Now the tendency is to just take whatever the very first thing we see and accept that as our answer. But if we do that, sometimes we're going to miss some important details. So read the first one and then find some others. Okay. So I come down here and I happen to know that this one is a pretty good link. Okay, a biconditional statement, P, if and only if Q, denoted P, if and only if, that's what this little arrow right here is, an arrow pointing in both directions. P, if and only if Q, is true when both P and Q carry the same truth value and is false otherwise. It is sometimes abbreviated as P, if and only if, or IFF, Q. Its truth table is depicted below. So not only do they describe what a biconditional statement is, they show us a truth table. Okay, now we know that a conditional statement is true, is only false, a regular old conditional statement is false, if the hypothesis is true and the conclusion is false. So here we have true, true, and the biconditional is true. Here we have true, false, and the biconditional is false. Here we have false, true, and the biconditional is false. Here we have false, false, and the biconditional is true. So the only way a biconditional can be true is if they have the same truth value, either both false or both true. And the reason for that, guys, is a biconditional statement works in two directions. It's both P, if P then Q, and if Q then P. So it's the original conditional statement as well as the converse paired together. So both statements have to be true. Now we know if we look at a truth table, okay, we look at if P then Q, okay, the way that this can be false is if P is true and Q is false. Well, if we look at the converse, it will also be false if Q is false and P is true. And so that's why for a biconditional statement, they have to have the same truth value, both P and Q. Okay? So we want to define what a biconditional statement is. It's a conditional statement that combines the original conditional if P, then Q. I'm actually going to toss out the whole thing. If P, then Q, and the converse. If Q, then P. Okay. Now, for conjunctions, we write P and Q. We use that little caret, and we read it P and Q. For disjunctions, we write P, and then we use that V, and we read it P or Q. For conditional statements, we use the arrow to denote if-then, or P implies Q. How do we write and read biconditional statements? And what's the abbreviation for that phrase? Well, if we look right back at what we were just doing, here's the denotation. Okay, the arrow that points in both directions. So, and we read it, excuse me, they said it also in here. It is abbreviated and it uses this phrase, P, if and only if Q. So we'll go right here. The statement that we use is P, or excuse me, is if and only if. The abbreviation is if with two F's, and we spell abbreviation correctly, hopefully. There we go. And the symbol, or the denotation, is the arrow that points in both directions. So if you have a pencil, you can draw that. Otherwise, we'll have to go to Insert Symbol, and there we go, the arrow that points in both directions. And we saw in our research as well that a biconditional statement is true when both the hypothesis and the conclusion have the same truth value, okay? either both positive or, both true or both false. Okay, but as long as they have the same truth value, then the biconditional statement is true. So each of these conditional statements down below are true. We want to write their converse, and if the converse is also true, then we want to combine the statements as a biconditional. If the converse is false, we want to give a counterexample. Okay? So two angles are complementary if their measures sum to 90 degrees. So the converse. Okay, now first off, remember, the conditional says if P, then Q. So we need to keep in mind that it's not necessarily the first part of the phrase that's the hypothesis, it's whatever follows that phrase if. So this is the hypothesis. So the converse, this ends up being the conclusion, and the two angles being complementary ends up being the hypothesis. So if two angles are complementary, then their measures sum to 90 degrees. Okay? Now, is this true? Well, complementary means that their measures sum to 90 degrees, so yes, this is true. Okay, then we want to write the biconditional, okay, which would be two angles are complementary if and only if their measures sum to 90 degrees. Okay. Next up, the Pittsburgh Steelers will have a 10-0 record if they beat the Jacksonville Jaguars. Now, once again, they put the hypothesis in the second half of the sentence. Remember, the hypothesis is always what follows the word if, not necessarily the first part of the statement. So when we write our converse, okay, we're going to say if the conclusion was the Pittsburgh Steelers will have a 10-0 record. So if the Steelers have a 10-0 record, then they beat the Jaguars. Okay? Now, is this statement true? Well, that's the only way that they can have that 10-0 record. Excuse me, if they have that 10-0 record, that means that they had to have beaten the Jacksonville Jaguars because they're their next opponent. So that has to be true. Okay? So the biconditional would be using an if and only if statement. So we can say the Steelers, we'll capitalize them, will have a 10-0 record if and only if they beat the Jaguars. Okay? Okay, moving right along. Two angles are congruent if they have the same measure. So the hypothesis. The hypothesis, once again, is always what follows the word if. Okay? So when we write our converse, okay, that hypothesis becomes our conclusion. And what was the conclusion, which is right here, that becomes our hypothesis. So the converse would be if two angles are congruent, then they have the same measure. Okay, we wanted to determine whether or not that's true. Well, two angles being congruent means that they have the same measure. So if we're told two angles are congruent, then they will have the same measure. So this is a true statement. Okay, and now we want to write the biconditional, okay, which would be two angles are congruent if and only if they have the same measure. Now notice if we type IFF for if, Word is probably going to catch that, and most spell checks will catch that as a spelling error because that's an abbreviation. It's not an actual word. It's just something that we use in geometry. So check your autocorrect settings because there might be a possibility that it changes IFF to just IF, and those are two very different things. So either make sure that you check your autocorrect so that it doesn't replace that, or stick with using the phrase if and only if. Okay? All right, so how about number 4? If a number is divisible by 20, then it is even. Okay, well, they have the if part at the beginning this time. Okay, so this is our hypothesis. So when we write our converse, we're going to make that then the conclusion. And the even part, that is going to end up being the hypothesis. So the converse of this statement would be if a number is even, then it is divisible by 20. And what do we think? Is this true or not? You think of your even numbers. Well, even numbers, you've got 20 is divisible by 20, 40 is divisible by 20, 100 is divisible by 20. But how about something like 4? Okay, that makes this false. Whoop, there we go. Okay, so a counterexample is 4, is even, but not divisible by 20. Okay, now remember, a counterexample is one where the hypothesis is true, so a number's even, but the conclusion is false. So 4 is even, but it is not divisible by 20. Okay? All right, next up. If x equals 5, then x squared equals 21. Okay, so the converse. Okay, I take the then and I make that my if. So if x squared minus 4 equals 21, then x equals 5. Okay, so if I go back to my original, if I take x and I put 5 in place of x in this sentence, x squared is 25, 25 minus 4 is 21. This statement is true. Okay, now if I go here and I solve this equation for x, so I add 4 to both sides, and I have x squared equals 25. Okay, and then I take the square root on each side. What I'll actually get is that x equals plus or minus 5. It's not just positive 5. X could be negative 5. Okay, so that's a counterexample. Okay, if I take negative 5 and I sub it in here, so negative 5 squared is 25. 25 minus 4 is 21. Okay, so this statement's true, and it doesn't have to be negative 5. So this is a counterexample, which makes the converse false, which means we can't have a true biconditional statement here. Okay, so this is one way that we can check whether or not a biconditional statement is possible. Rewrite it using the converse, and if it's true, then we can write it using the phrase if and only if. Okay, if we write the converse and it's false, then all we need is a counterexample to show that it's false. Okay? All right. So number 6, we want to write an example of a true biconditional statement. Well, I have an example for you, so you can come up with your own. Okay, you will earn an A if and only if you score a 90% or better. So if you score a 90% or better, you will score an A. Okay, it works in both directions. That makes it a true biconditional statement. Number 7, they want us to write an example of a biconditional statement for which the conditional is true, but the converse is not. Okay, so here's what I'm going to do. I'm going to give us a conditional and a converse. Okay, now I want you guys to come up with your own on yours. Okay, but here's a conditional. If a quadrilateral is a square, then it is a rectangle. Now someone's going to argue with me on this and say that, well, a square is not a rectangle because a rectangle has 2 long sides and 2 short sides, and a square has all 4 sides the same length. Guess what, guys? A rectangle does not necessarily have 2 long sides and 2 short sides. If you don't believe me, okay, the definition of a rectangle is just a quadrilateral with 4 right angles, and that's it. Okay, it doesn't necessarily have anything else about the side lengths, just that all 4 angles are right angles. Okay, there's your answer right there. So if it's a square, then it has to be a rectangle because a square has 4 right angles. Okay, now the converse would be if a quadrilateral is a rectangle, then it is a square. And I think we can all agree that this does not necessarily have to be true. Because like we just said, a rectangle, the definition of a rectangle doesn't say anything about the side length, but part of the definition of a square is all 4 sides have to be the same length. So this would be an example of a false biconditional statement. So a quadrilateral is a square if and only if it is a rectangle. Okay, this would be a false biconditional statement, because while the conditional is true, the converse is false, and they both have to be true in order for the biconditional to be true. So a biconditional statement is a statement that combines the original conditional, if P then Q, and the converse, if Q then P. Okay, and they both have to be true. Okay, we use the phrase if and only if, which we can abbreviate IFF, and we can use the arrow that points in both directions as a symbol for it. A biconditional statement is true if both the hypothesis and the conclusion have the same truth value. Compulsion, conclusion. They have the same truth value. They're either both positive, or excuse me, both true or both false. Okay, if they're both true, the biconditional is true. If they're both false, the biconditional is false. But if they have two different values, one's true and the other's false, then the whole biconditional is going to have to be false.